Hello, today we're going to cover 6.3 in college algebra. So far in chapter 6, we've learned about exponents. We talked about their important features, how they were continuously increasing from left to right as long as our base was a regular, normal, greater than one base. The domain was all reals, but we said that it did have the horizontal asymptote along the x-axis that kept the range above 0, always positive, because these negative exponents would just flip them over, but they would never make it turn into a negative value. We said that everything was pretty much the same if our a was a fraction or decimal smaller than 1, except it ended up as a flip from left to right, so it ended up as a decreasing function. So remember that they always had that y-intercept of 0, 1 because anything to the power of 0 was 1. So all of this is important because in section 2, we started talking about the inverses. We said we could inverse anything that was 1 to 1 by doing a flip of x and y. So we just exchange the x and the y. Well, luckily all of these exponential functions are 1 to 1. So even though it gets really thin right here, it's never actually crossing the same horizontal line more than once. So now in 6.3, we're going to take the inverse of an exponential function, which is a logarithmic function. Now, for some reason, logs seem to scare people. I think it's because they think it's a word problem, because you see log and you think it's a word. But I guess they just ran out of mathematical symbols or something. So just like a plus sign or a minus sign or a divided sign or an exponent, it's just the same thing. It's a symbol, it's an operation, it's the logarithmic operation. In fact, it is the backwards operation from exponents. So we can flip back and forth between exponential function or exponential notation and logarithmic notation. Just like if I told you that 2 plus 3 is 5, I could give you that same piece of information by saying that 5 minus 3 was 2, kind of the backwards. Either you put them together to make 5 or you take them apart to find one of the two pieces. So it's that same idea. These are the same pieces of information in two different forms, addition form or subtraction form. So we can take our exponential form and flip it into logarithm. Now, everything we just learned in exponential functions gets flip-flopped in the logarithmic functions. Remember when we talked about the one-to-one flips, that we saw a reflection in the diagonal y equals x. So everything that was right here on an exponential function xy gets flipped over here to the logarithmic function as a yx. That means we learned that the y-intercept over here of 0, 1 was consistent among all exponential functions because anything to the power of 0 is 1. So that means on a logarithmic function, it gets flip-flopped, and they will always have an x-intercept of 1, 0. So instead of 0, 1, we have 1, 0. It flip-flops the x and the y. On this one, we talked about how it never seeped into the negatives that have this horizontal asymptote right here along the x-axis where the y is 0. It never crossed over into the negatives. So that means over here, our logarithmic functions have a vertical asymptote where the x is 0. So because of that, the x's never switch over into the negatives. On the exponential, we had a domain of all reals because we could put in any x, but our y's were limited to the positives. So we flip-flop that in the logarithmic, and our x's are limited to the positives, and our y's are all reals. So we can go down as low as we want. And even though it ends up being kind of a steep, or in this case, I guess, shallow curve, you can actually reach any y value. You just have to go way, way out on your x values. And that's basically it. The logarithmic function is everything about the exponential function flip-flopped. So we have all of those same features. So what we're going to do is we're going to learn how to flip-flop it, how we're going to put in that form, and then some of the kind of key features and specific examples that we're going to run across. So in this one right here, we have the following graph is an equation of the form this or that. So basically, does it look like the blue line or the red line over here? So of course, we see he's got this vertical asymptote instead of horizontal asymptote. He's got this x-intercept instead of a y-intercept, so it must be a logarithmic equation, not an exponential equation. It also wants us to find the b. Now, in our exponential function, we found that anything to the power of 1 was just itself. So right here at an x value of 1, we could pretty easily spot what the base was because anything to the power of 1 was itself. So that means right here at this point of 1, 2, I found the value of the base. So 1 would always show us what the base was. So same story over here, I can spot that base by finding the y value of 1. So the base would be found whenever the y value is 1. So on this one right here, you can see that it's the corresponding logarithmic form to this blue one. So this one had a base of 2. So let's check this one. Let's see what his base is. So I need it along the y value of 1. So I kind of skim across and you can kind of see it got a little sloppy there, but they intended for it to hit the crosshairs right here. So this has a kind of an intercept of y equals 1, an x value of 4. When the y value is 1, the x is 4. So that means the value of the base is 4. So this one could be written as the equation y equals log base 4 of x. Now I know that seems a little weird. This is just a special notation that's going flip-flopped from the exponential notation. We're going to talk about how to flip-flop it. So skimming through these, let's see if we can spot the graph or the right one where the log is the base of 9. Well, first off, I see that it's a log, so it's exponential. So it's logarithmic, not exponential. So notice in these two graphs, they have a horizontal asymptote, not a vertical asymptote. So one of them did get flipped over the x-axis, so it must have had a base smaller than 1, but both of these have the horizontal asymptote. So these are both exponential. So these are not the ones we want because they're both exponential, not logarithmic. So now I have these two to choose from. Now of these two right here, they're both logarithmic, but I want the one that has the base of 9. So I would need to skim across the value of 1 until I found the 9. Now you'll notice that they actually don't have x's that go out to 9, so you might think we're stuck, but looky here. This looks a whole lot like the one we just did, and it has already crossed the y value of 1. So this one has a base of 4. So he's not our guy because we wanted a base of 9. So that means by process of elimination, it must be this guy. And from kind of looking at it, you can tell that it's getting really steep, but it looks like it'd probably be about 9 when this red line crossed the value of y equals 1. Okay, so that's just kind of looking at it really generally from the shape of the graph. So now let's talk about more specific features because of course we're going to be doing more calculations. Keep that calculator handy because we are going to be doing lots of calculations and there's lots of cool buttons that I'll show you tricks. Now the main thing that we're going to use to start out is switching back and forth. We are of course more familiar with the exponential form than the logarithmic, but luckily we can go back and forth. So we can kind of keep playing with that exponential notation that we're more used to until we get more used to the logarithmic. So in this example down here, we had it in logarithmic form. Let's swap it out. So using this pattern up here, we can swap these into either form. So right now down here, he's in this log base a of x equals y form. So let's switch him out. So this says that we can take the base, which this little base a right here, would be raised to the power of y, the one on the other side of the equal sign. And then that is set equal to x, the one inside the thing that the log is taken of. So let's switch this out. So this would be written out exactly the same as 4 to the y equals x. So that means all of these points could be found by taking this pattern. So I would raise 4 to the power of y, and that would give me the x value. It's flip-flopped. So let's test this out. If I raised 4 to the power of 0, because this point right here has a y value of 0, then sure enough, that would equal 1. If I raised 4 to the power of 1, like this point right here, the y value of 1, sure enough, that equals 4. So these 2 points that we have tested work out. These two are the same exact information in 2 different forms, logarithmic, exponential. Okay, so let's practice just that, flipping them back and forth. So this one is an exponential form. Let's switch it to logarithmic. So the first thing I do is I write out log because I know log form has a log. The little base to me is the easiest to spot because that's the one that has the exponent. So the base would be a 2. So I make a little 2 right here. And then I always remember that the others are a little bit backwards from what they seem. So it's log base 2 of 16 equals x. The logarithm always equals the exponent. A logarithm is an exponent. So the logarithm always equals the exponent. And that's it. That's all you need. It's in logarithmic form. Same information. Let's try it again here. So first thing I write out log because I know it's a log. I'm switching it to log form. This one would have a base of 10 because 10 is what has the exponent. Remember that it's going to be equal to the exponent. So that negative 3 is going to be over here. So that means this would be log base 10 of the decimal 0.001. And that's how you would read it. Log base 10 of 0.001 is negative 3. Okay, now this one over here, I've got a log. It has a base of the number e. Remember that e is a number, not a variable. It's that weird number 2.71 blah, blah, blah. Okay, remember that it's a little backwards. So log base e of 70 equals the exponent t. Okay, now in parts B and C here, these are 2 of the special cases, and really there's only 2, so don't panic. Okay, there's a very limited number of rules for logs, which is why they're one of my favorite sections, because there's just this handful of rules, and you can do pretty much every single problem with these just handful of rules. There's no weird variations, no tricks. If you remember this, just a few handful of rules, you can do every single thing. So one of the little handful of rules is that the 2 special cases are log base 10 and log base e. They give them special names, and that helps us to use our calculator. So log base 10 can be written without the log. It's kind of like the ninja number. Since we have 10 fingers and we use the base 10 number system, if there's no number here written, it's implied that it's just normal, regular base 10, because that's what we're used to, base 10 numbers. So if you ever see a log without the little number there, just know that it's implied that it's 10. So the little e pops up quite often. So anytime that it's log base e, just to avoid confusion, since it's another letter, they gave it a special name called the natural log. And I guess they were, they named it on backwards day, because then they named it ln instead of nl. But the natural log, ln, is specifically log base e. So I think they did that probably just to avoid confusion with the letters. So let's write these in their special form. This one would be just log of 0.001 equals negative 3. And then this one we could also write as ln of 70 equals t. And they're the same thing. It's just another form of the same thing. Now this one, just to double check and why it's important to know this, on your calculator, you'll find the log button right there next to the 7. So go ahead and hit the log button. And let's just try this out. So log of 0.001. Careful with those zeros, make sure you have the right number, 001, and hit enter. And there he is, negative 3, just like we expected. You'll also see the ln button right below it. And so these are the 2 most common logs, which is why they gave us special buttons for those. That's why it's so important to know these special cases. Next, let's go the other way. So if it's in logarithmic form and I want it back into our more familiar exponential form. So remember that the base was that little number. Remember that it was equal to the exponent, which made it a little backwards for the 32 right here. So I kind of remember it as I untangle this circle. So 2 to the 5 equals 32. It's kind of a big knot. And that's it. And this is something with all numbers, so you could even double check yourself and check that 2 to the 5th on your calculator, hit enter, and sure enough, it's 32. This one has letters, so you couldn't really double check yourself, but anytime you can, that's a good way to check. So this one would be a, base a, to the power of 8 equals q. Remember, the logarithm equals the exponent. These are a little bit backwards, so just be careful. And then this one right here would be that little t to the power of x equals m. Okay, so using our newfound knowledge, let's see if we can evaluate some logs. So this one we're saying the log base 4 of 64 equals what? I'm going to name him x just to give ourselves something to go by. So we're looking for the exponent. 4 raised to the power is 64. So let's switch it back to exponential form because we're a little bit more used to that. So it'd be base 4 to the power of mystery number equals 64. So hopefully you memorize those numbers like I recommended, and that would help you to see that 4 squared is 16, but 4 cubed is 64. So the power that I would need to plug this in and make it work out is a 3. Okay, so this one right here, same story. I'm going to name it an x again. Switch colors so I can distinguish them. This one would be 4 raised to this power equals 1. And I hope everybody gets this one because anything to this power should equal 1. What is that number? It is 0. Anything to the power of 0 equals 1. Okay, now this one we've got 2 layers, but we remember that order of operations, we start with the inside. Okay, so I'm going to see what is this little inside part equal. So I'd ask myself 2 to the power of this equals 128. Okay, it's a little sneaky, but we could count up 2, 4, 8, 16, 32, 64, 128. So 2 to the 7th power is 128. Okay, so that means this inside stuff is a 7. So the rest of the question asks us log base 7, and that inside stuff was a 7 equals what? So let's name this what? The letter y, just to specify. So 7 to this power equals 7. So hopefully that's easy. 7 to what power equals itself? That would be a 1. So the final answer to this question is 1. Okay. Next, I've got another 2-layer one. So first I'm going to do the inside only and ask myself 3 to what power equals 81. Okay, I could count up or I could use my calculator. 3 squared is 9, 3 cubed is 27, but 3 to the 4th power is 81. So that means inside of this parenthesis, the answer of that part would be 4. So the rest of the question says log base of 1/2, so fraction 1/2, equals 4. Now this one's a little sneaky, so stick with me and don't panic because there is a shortcut that I'm going to show you. Okay, so follow with me so you can see the reasoning, and then I will show you a shortcut to help you out with this. So we're asking ourselves 1/2 raised to this mystery power should equal the whole number 4. And remember, this whole number 4 would be 4 over 1. Okay, so basically I would need this 2 to flip over. And what kind of exponents make something flip? The negatives. So not only does it need a negative, but he needs to go from a 2 to a 4. Well, 2 squared is 4. So I would need to have him flip and squared. Okay, that one's a little sneaky, but like I said, don't panic. I'm going to show you another way to get this. All right, last one's a 3-layer. Okay, we got this. So first on just the innermost, so we're going to call this little guy x. And see if we can figure out 5 to what power equals 125. May not know off the top of your head, but you can count it up. 5 squared is 25. 5 cubed, sure enough, is 125. So this innermost part right here is a 3. So let's rewrite it. So next I have log base 2 of log base 3 of 3. The innermost part was 3. Well, log base 3 of 3 sounds kind of familiar. Hopefully you know that one. So if I said that this part was equal to y, then 3 to the power of y equals 3, and anything to the power of 1 is itself. So now we're left with log base 2, and my answer to that one was a 1. So now we're asking ourselves 2 to what power equals 1, and hopefully you remember from this one back here, anything to this power is 1. So 2 to the power of 0 is 1. The final answer to this problem is 0. We started from the innermost and worked our way out. Okay, let's try a few more like that. And like I said, I do have a shortcut, not necessarily a shortcut, but a trick for some of the trickier ones. But sometimes working it out like this is actually faster and easier than trying to punch it in the calculator and risking a mistake. So if you can tell off the top of your head that anything to the 0 power is 1, go for it. Okay, now this one, it's in the logarithmic form. I'm going to switch it back out to the exponential form to see if it's more familiar. So the base of 3 to the power of 2 equals that inside x. Remember, it always equals the exponent. Well, look at there, this one's already solved. I just need to evaluate 3 squared, which is 9, and I'm done. There's the answer. So it really just took me putting it into exponential form, and then I was pretty much there. This one I go, like all these that we were doing a minute ago, 3 to the x equals 81. Well, that looks pretty familiar. That was actually one we did earlier. We already decided that 3 to the 4th power is 81. So the answer to this x would be 4. Next, I've got this one. So it's in logarithmic. Let's switch it to exponential to see if that makes life easier. 4 to the power of -2, always equals the power, equals x. Okay, well, 4 to the -2, that's the flipper, would be 4 squared flipped over, be 1 over 16. You can also use your calculator and run a math inner. It should give you that same thing. We've got fractions, but don't panic. This one, we take the base of 2 to the power of x, this time it's the power that's a mystery, equals 1/4. That kind of looks familiar, looks a lot like this guy. So this whole number 2 needs to turn into a fraction, so he needs to flip over, and just like last time, it needs to go from 2 to 4, so that x must be a -2, flipped over and squared. Okay, and then last we've got 27 raised to this mystery power equals a 9. Now this one's sneaky, and here's another one that, don't worry, there is a backup coming, but let's see if we can reason through this. Now most of the time exponents make it bigger. There were the exceptions where it flipped over, and there was one more rule that we learned about that made things change, different kinds of exponents. So something that would make it get smaller. So you can kind of see that they revolve around a 3. 27 is 3 times 3 times 3, 9 is 3 times 3. So what's happening is that we would actually have to take the cubed root of this number. So the cubed root, remember, could be expressed as an exponent of 1/3. So the cubed root of 27 could be expressed as 27 to the power of 1/3. Now that gets us closer, but not quite there, because the cubed root of 27 is 3. So we're closer, but that's not quite what we needed. We needed 9, but 9 is 3 squared. So the cubed root of 27 squared would be 3 squared, which is 9. So there it is. So I need this exponent right here to be the cubed root squared. So this x would need to be the 3 on the bottom, the cubed root, and squared, 2/3. Whew, I know that one was sneaky. So here we go, let's learn that back up. Now this leads directly into the next section, so we're going to learn more about this section on the next video. But basically right here, this special change of base formula. So I call him my log splitter, because right here we've got 1 log. I take my little tiny mathematical chainsaw and go, and he turns into 2 logs, just like this, my tiny chainsaw log splitter. If you have the newer, latest, greatest technology calculator, there is going to be a button for this, but I'm going to show you both ways depending on what you've got. So in your calculator right now, hit the button Math, just like you do for your fractions, and scroll down to the bottom. If you have the one that's called log base, then you're in luck. You've got the latest, greatest. Life is going to be just a little easier for you. So go ahead and hit enter on that one, and it should look like this right here. If you have that button and it doesn't look like this right here, come see me, because I can fix that for you, okay? But if you don't have that button, or you don't have a way to come get me to fix that for you, here's the trick. Don't worry, you're not doomed. You just have one extra button press. So we're going to use the log splitter right here that says with that teeny tiny mathematical chainsaw, we go and we turn it into the log of m, there he is, over the log of b. There's the b on the bottom, there's the m on the top. Two separate logs. So what happens is you can change the logarithm of any base to any number to two separate logs with the same matching base. So that same matching base is our safety, because in our calculator we have some already established bases of 10 and e. So basically we get to use this right here to change any unknown base into one we have a button for, ln of m over ln of b. Or if you just like it way better, you could also use your log button, log of m over log of b. And let's go try it real quick with those two sneakier ones. So let's say we'd gotten stuck on these last two, the one with the fraction, the negative exponent, or this one with the roots. So say we'd gotten stuck. So on this one right here, let's try that log splitter. Okay, so right here, I would go log of the 1/4. Okay, I'm going to use my log button, and then I'm going to divide it by log of 2. Okay, so I use my log splitter and go with my chainsaw. He's on top, he's on bottom. Okay, so typing this in, write it just like me. So you hit your log button first, log, type in the 1/4, 1 divided by 4, and make sure right here that you close these parentheses. So you have to close these parentheses or it will mess up. Okay, watch that, close parentheses, just like this on my screen. Okay, if you forget that close, everything will go wrong and you'll get the wrong answer. And then I hit divided by, and I go log of 2. Okay, so you have to get that closed parenthesis right there after the 4, it will mess up. You should close the very last one, but it's actually not as essential, but it will mess up if you forget the 1 after the 4. Hit enter, and there's that same answer we just got of -2. Magic. So let's try this one here, just in case we got stumped on the roots. Okay, say we forgot about that rule. So I could use my little tiny chainsaw, where the 9 is on top and the 27 is on bottom. Now remember, when you split this log, there's 2 logs. So I would write it out as log of 9 over log of 27. Don't forget that there's 2 logs, and don't forget to close this parenthesis right here. So type it in just like that, log of 9, close parenthesis, divided by log of 27. Don't forget that parenthesis right there after the 9. Don't forget your divided by. Log splitter. Enter, and then it gives you the decimal with the math inner of 2/3. Okay, real quick, if you have that magical button, let's practice that. Hit your math button, scroll down to that one that says log base, and then it should give you those bubbles that you would just fill straight in. So I would put the 27 as the little number on the bottom. I would put the 9 as the number there on the side. And then I hit enter. And it gives me again that decimal version of 2/3. So I can hit math, enter. And it gets it right back out for me. So that is your backup. It's the log splitter. That is called the change of base formula. So we're going to talk about the rest of the properties on section 4 video, but I did want to show you that shortcut so you can get started on it on this section.